Morning, everyone. Sorry about being 7 minutes late. I actually started logging in at 9:18, and I've been trying to get my computer to run and all that stuff since then. I apologize, everyone. I don't know what's going on. Still got people coming in. So there's Gunner. All right, well, let's before we get started, does anybody have any questions? I know I had some emails, for instance, from various people that didn't hear me tell everybody that the test had been moved to a week back. So the test and the practice tests, I'll have them up in between lecture and lab today. I logged in early in hopes that I could go ahead and post them. But like I said, I've logged in at 9:18 and just now got in. So I wasn't able to do that, but I'll do it between our lab, my next class, and our lab today. So you'll have them and see them there by the time you go to lab at 1:30. Those of you who have me for lab. By the way, is there anyone in this class? You can chat to answer this. Is there anyone in this class that doesn't have me for lab? Looks like everybody does. Okay, I thought that was the case. We tried to make it this semester where everybody that has a certain person for lecture has the same person for lab, but there were some people that begged to take a different section, and I think I allowed one or two, so I was trying to figure out what was going on with that. So I'm taking it no one has any questions regarding course material, that sort of stuff.
I do have one, Professor.
Go for it.
All right, cool. So you remember how last week on Thursday you did those like six examples of like finding different like either total distance or acceleration and all those kind of things. Where did those questions come from again?
I made those up. They're actually were on a Word document that I had typed up. I thought I put the Word document on the Google Drive. If not, I will check and see if it's not up there, and I'll put it up there for you.
All right, cool. Because I have all these formulas and examples and stuff, and I don't know where the numbers came from. Yeah. Appreciate it.
No problem. Yeah, I'll like I said, I think I put them on Google Docs, and I'll label them like I normally do with the class. With the class, I label it PHY241. Actually, I just noticed I got a typo on my typo. I got a handwritten note on my notes. It's 241D01B. And then it'll be like the file name will be _0125 for today, 22. But that day, of course, was the 20th. So it'd be 012022. Okay.
Yeah. Okay.
And you know how to get to my Google Drive, yes?
Well, yeah, I printed out the formulas, like all the examples, okay. But like right next to the examples, all I have is there's 118, 2020. 22, and then there's 242 next to it. So the Word doc isn't on there.
Okay. I'll watch out also sometimes, like I did for my notes this morning, sometimes I'll put 242. If it has a 242 and it stayed in the 241 thing, it might actually be a 241. So it could just be a misprint. Normally I catch that and I go and put another copy of it on there, but I'd never assume that I'm that it's absolutely that. Look at it before you download it if you want, or if it doesn't take much time to download it and then throw it away if it's the wrong one.
Okay, well, I'm looking at the 242 thing and it says something about voltage and electrical.
Yeah, that's not the one. So yeah, that's definitely not the right one. No problem. Yeah. I will make sure it's up immediately. I didn't get the notes up until last night, I think, or maybe it was the day before yesterday, for the last class, which was on the 20th. But they're up there now, and now I got to make sure the actual problems 1 through 6 is up there as well. But I'll do that along during the time between my lab and my lecture, and I'll write a note.
Okay, thank you, Professor.
Gotcha. No problem. Anybody else have a question? So the test now, test 1, I pushed it back a week. It will be due basically 11:59 p.m. on Monday, but it'll come up today. The practice test will be up today as well. And practice test 2 will be up today. I apologize. I don't know how that never had those practice tests in there, but I've now got them moved over. I just have to make them available to you and check them, make sure they're right. Sometimes when I move them from another course, I get there and it looks like a whole test, and then I open up the test and there's no questions in it. So I got to make sure that didn't happen again. I haven't quite figured out why it does that, but it's a particularly useless feature of Canvas. So we got to figure out how to deal with that. We have essentially finished all of the work from the chapter 2, which was describing motion and specifically kinematics, but I wanted to give you a little typical problem that could happen. So for instance, you could have, I want to turn the document cam on now. Part of the reason that I'm doing the wrong thing, no wonder. Part of the reason that I did that derivation, show you how we got the equation x equals 1/2 at squared plus v0t plus x0. Part of the reason that I showed you how I derived that is because in reality, you can be given any acceleration a and should be able to know how to do that. So if we found, for instance, that a is equal to some constant c times t, the square root like that, then we should be able to actually find out what the velocity as a function of time is. So for instance, we know a is equal to dv dt. We could then say, okay, well, dv dt is equal to square root of ct. And again, c is a constant. And it obviously has units of meters squared per second squared, meters squared, that's got to survive that, per second cubed. Okay, so in order for that to work out to have meters per second, I've got to have those units. So just to let you know that. So what we can do now is we can say, okay, well, I'll multiply both sides by dt. That'll get me dv is equal to the square root of ct times dt. I integrate from v equals v0 to v, and that's technically meant as v of t, but I'll just write it as v from here on out. And then this one's going to be integrated from t equals 0 to t. So this side just becomes v of t minus v0 equals, and now I have the integral of something to the 1/2 power. Well, we know that the integral of something to the 1/2 power is pretty straightforward. We're just going to add 1 to the plus 1/2 because that's what the power is, and that'll be plus 3/2, and then we're going to divide by that plus 3/2. So that'll be plus, well, actually, first I got to say let, just for ease, let u equal ct, then du is equal to c dt. So in order to make up for the fact there's a c under there, I really need to put a 1 over c here. So I'm going to say plus 2 over 3c, and then that's going to give me the square root of ct. Or actually, I'll write it this way. I was going to cube that, but it might be better just written like that. And then I got to evaluate that from t equals 0 to t, which you can tell is just going to be ct. So that's going to be v is equal to v0 plus 2/3 over c times ct to the 3/2 power. Now, in principle, you can next say, well, v, which is really v of t again. Notice I went ahead and wrote it as just plain v there, but it really is v of t. That's equal to dx over dt. So that tells me dx over dt is equal to v0 plus 2 over 3c ct to the 3/2. I multiply both sides by dt. I get integral dx from x0 to x of t is equal to integral t equals 0 to t of v0 plus 2 over 3c ct to the 3 halves dt. Again, I let u equal ct, then dt is equal to du over c. In other words, I went ahead and skipped the step, took it from that and divided it by dt. So this dt is really just du over c. So I had to add another c on that. With the screen, have you tried clicking on the screen so that it becomes your main screen? Or if you're using my phone, it's got to stay a small screen, of course. But yeah, I just got the first message saying that the internet connection was unstable. Let me see if I got any other apps running. Sometimes that can cause problems. I don't believe I do. Nothing else is running. All right. It looks like everybody's having the same problem. This is what I've written so far. See if this helps you. So I was telling you I derived this for a reason, not only to show you how we get it, but to make some argument about how you can get kinematic equations for any acceleration situation, like the acceleration equals the square root of ct. Since a is dv dt, that creates what's called what is a separable differential equation, a very simple case. And I just basically multiply both sides by dt. That would cancel out the dt here and give me this, but then I integrated it using substitution u equals ct. So I have u to the 1/2 power. It's even bad now, even when I'm holding it up close, Wyatt. Okay, so the internet really is crap right now. Hold on just a second. Okay, I'm back. I'm wondering if my daughter might be mistakenly using the internet, and that would cut up on it. Let me. Hold on a second. I'm still working here. I wonder if that's the problem I had this morning when I was trying to get on. Did you get my text? Okay, just make sure you're not on the internet or playing any games or anything, because it's killing my class. Okay, later. Evidently that was not it. My daughter, she was asleep, so Anyways, okay, and everybody says it seems back to normal. Okay, so what I was saying was we took the fact that A is dv/dt, and I gave you an argument for what an A equals. Specifically, that'd be like a square root. So it'd be something that rapidly goes up, but then it would start to level off, but never really go to zero. That's why this might be a fairly realistic one. When I put it on the other side, then I can integrate by multiplying both sides by dt, integrating it using the substitution u equals ct. I got this expression. Now that's velocity as a function of time. So I set that equal to dx dt, and I integrate it again. And now you can see I will get x of t minus x0 is equal to, this will be v0t when I integrate that and go from 0 to t. When I integrate this, this will be plus 2 over 3 c squared, because I have to do another substitution. Ct equals u, and that makes this dt into c. So now I've got a c squared in the bottom, but now I'm integrating u to the 3/2 power. So that's going to be 3/2 plus 2/2 will be 5/2. So this will be, I'll be 2/5 times ct to the 5/2. And that's already evaluated at t equals 0 and t equals regular t. So I can now finally say x is equal to this 2 and this 2 is going to multiply. So I'll have 4 over c squared 15, 3 times 5 is 15, times ct to the 5/2 plus v0t plus x0. So we've just made up a whole new set of kinematic equations just from using an acceleration as a function of time. Now, if I wanted to, I could take this equation right here, solve it for t, plug that into into t here, and then attempt to solve this again for something, and that might give me another kinematic equation like the one we had before, which is v squared equals v0 squared plus 2 times a times parentheses x minus x0. So that's basically a process that you should know, and that's pretty much all I wanted to make sure you covered with regards to chapter 2. I think you can figure out the related rates problem, or excuse me, the relative frames problem. So for instance, when you have a boat riding on a body of water, and that's like a lake or a stream or something, that body of water is moving, and that's a moving reference frame. And the boat moves with respect to that water, but it also moves with respect to the land. So you've got to be able to do problems like that. And I gave you the idea that, let's see, the velocity, this is called relative velocity. I gave you the one equation I think's most important, and that is the velocity, let's say, of the boat with respect to land is the velocity of the boat with respect to the stream plus the velocity of the stream with respect to land. The main thing is this is a stream and they match. In other words, these two inner symbols have to match. These two outer symbols have to match these symbols. And that's a vector equation too. So I can put a vector symbol over top of it, and then you just add them like vectors. So that's the way you work out relative velocity. You have to state it as what you're wanting to know the velocity of and with respect to which frame. And then you can always make up an equation by making sure the first symbol is the first symbol and the last symbol is the last symbol, and the two match. The only other rule that really comes in super handy that you'll need is the velocity of A with respect to B is equal to the negative of the velocity of B with respect to A. So sometimes you might have the velocity of the stream with respect to the boat, or you might have the velocity of the land with respect to the stream or something weird like that. If that's the case, you can replace it with a negative and then flip the signs. So these two in conjunction with each other really help to solve those relative velocity problems. You'll see in the homework, so those are really trivial. Between that and the examples in the book, I think you have plenty of experience to see them. And I did a couple on my YouTube channel. So as I suggested, y'all might want to at least subscribe to my YouTube channel while you're in class. So every time I post a new video, you'll get a email saying that you got one, or a text message, or whatever, however you set it up. All right, I'm hearing that the screen has gotten small again. Well, the good news is this is going to be a somewhat of a refresher. We're now going into chapter 3, which is about vectors and 3 dimensions and stuff like that. So we're going to first do vectors and how they're added, and then we're going to go into projectile motion, which is basically using these kinematic equations that we derive, not these newest ones. Those are just made up for an example. We're going to use kinematic equations for both the x coordinates as well as the y coordinates. In other words, there'll be a horizontal motion and there'll be a vertical motion. And the most amazing thing about projectile motion is that the horizontal motion is completely independent of the vertical motion, so that you can just treat the horizontal motion, if you're ignoring air resistance, as an object moving at a constant velocity to the right, say. And then you can treat the vertical motion as if it were an object being thrown upward. And what dictates how far it goes is how long it's in the air. And how long it's in the air comes from the vertical motion. And how far it goes to the right, say, during that time is the horizontal motion. So you take the vertical motion, solve for time, then take and plug that into the horizontal motion equations, and that'll tell you how far it goes in that amount of time. So that stuff's pretty easy, but it's, it's different because you got to work 2 problems at once. So let's start again, as I said, with chapter 3, and I'm going to start off with vectors. Okay, so the main thing is a vector, just like vector on Despicable Me. Anybody remember how Vector, the bad guy, defined himself to Gru when he first met Gru? He said, it's a mathematical term. He said, it's because it's a vector and it has magnitude and direction, and that he does evil with vector and, or excuse me, with magnitude and direction, or something like that. So that was actually a correct definition of a vector. A vector is a thing that has both a magnitude and direction. The direction is indicated by like a compass heading, or in the XY coordinate system, you can say measured counterclockwise from the positive x-axis. Or with a compass, you could do it. There's a couple different ways, to be honest with you, several different ways. You can set up an XY coordinate system like this. Okay. And if someone tells you that the vector just points at 30 degrees, then that automatically, if that's the only thing they say, that automatically means I'm measuring up counterclockwise from some arbitrary x-axis that I draw, and I go up 30 degrees. And that's the direction of the vector A. Okay. And then we'd say this length right here is 10 newtons, and that's called the magnitude. And it cannot be negative. So you cannot have a negative magnitude ever, 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 ever. Now, the thing about vectors is there's other ways of notating them as well. You could also call this north and you could also call this 0 degrees. Then this one would become east and 90 degrees. This one would be south and 180 degrees. And this would become west and 270 degrees. Okay. So another way of expressing this is compass heading of 60 degrees. See how different that is? Exact same vector, notated a different way. I could also say A is 30 degrees north of east. I could also say A is, whoa. Sometimes my letters and numbers get mixed up. Does it, y'all ever do that? I just wrote a S for 60. Anyway, 60 degrees. In this case, it would be east of north. So that's a bunch of different ways you can actually indicate a single vector. I could even say A is, and this is really bad, but negative 390 degrees.
Just a quick question.
Yes.
I can't really read. It says at 30 degrees, like the first one.
Uh-huh.
It's at 30 degrees, and then what did it say?
At 30 degrees is 10 newtons. Magnitude is 10 newtons, and magnitude cannot be negative.
Right. Okay.
And hopefully
And that was just the distance. That's just an example.
Gotcha. Yeah, that was just an example. And what I then did was show a bunch of different ways we can express that exact same vector. So A is 10 newtons at a compass heading of 60 degrees is the same thing. A is at 30 degrees north of east is the same thing. A is at 60 degrees east of north is the same thing. And A is at negative 390 degrees is the same thing. So remember when you measure, actually not 390, made a mistake there, 330. Everybody make sure you made that change. Because when you have a negative angle and you don't state anything else, that means you're going clockwise, or excuse me, clockwise from the positive x-axis. So all these angles measured this way are negative. So I stopped just shy of 360 and went to 330. So that's another way of expressing it. And this is often written whereas this one's often written catch that, I wrote it in the wrong order. N-O-E, and this is E-O-N. In other words, you just take the first letter of the word. So north of east, you don't have to actually physically write north of east. You can write N of E or N-O-E. And the same thing with this, E of north. I usually take the time to at least put an F in there so you can see it's N of E. But those are all a bunch of different ways to express magnitudes and directions. The magnitude is just going to be like a length unit. It doesn't have to be length because we could be talking about something abstract like a force, in which case its units would be newtons. But it could be a length, in which case it'd be meters or kilometers or whatever. It could also be anything really. You could, there's ways in which you could even picture temperature as a vector, in which case you could have Kelvin as a direction. But again, we're just never going to have a negative magnitude. Now, some more things we need to know about them is, remember, they have vectors have magnitude and direction. So if you need to work with them, since it has these two quantities, and I haven't told you about any other qualities of it, as long as you don't screw up these two qualities about it or these two quantities about it, then you're not messing up anything. So you can take a vector. This is under very specific circumstances. You can take a vector A and you can move it anywhere you want. So here's A. I can just move it over here, and long as it's still the same direction and the same magnitude, then I haven't altered the vector. Okay, that'll help when we go to do things like adding and subtracting. Say can move as long as you do not mess up the direction or magnitude. Okay, that'll come in handy in a little bit. Now that there's a rule that's with that when we're talking about, when we get later into say gravity, there's going to be something called a gravity field. You can't just grab a vector at one point in space and assume that if you move it to another point in space, it's going to be the same thing, same magnitude and direction. That's because that's a vector field, not a vector. A single vector, you can pick it up and move it around. But if it's a vector associated with a field, each particular point in space, every X, Y, Z in space is assigned a very specific vector, say V. So that doesn't always hold, but the good news is we're not going to deal with that for several chapters. Okay. So generally in these early chapters, you can move them around. Not only that, another good thing about vectors is they're modeled on like taking trips. Our vectors can be modeled with taking, let's call it walks, say. So if you get up in the morning and you walk 10 meters east, okay, and then you hang a left and walk 20 meters north, and then you walk, let's say 10 meters at 30 degrees south of east. You draw a little coordinate system here, you go down 30 degrees. And then that's this vector, okay? All you have to do is just keep those strung along with the head, the tail, then the head of this one to the tail of the next one. And your resultant, your addition, is just a vector drawn from here to the last one. This is called the resultant. So if this vector was A, this vector was B, and this vector was C, then the resultant R is equal to A plus B plus C. Now, if I use the rule I just learned about vectors can be moved around, as long as you don't mess up their magnitude and direction, then I could also see that if I first did 20 meters and then did 10 meters and then did 10 meters, we can see that that's equal to B plus A plus C. And in fact, that's a rule. You can see that the order of addition is irrelevant. You can go in any order. So A plus B is equal to B plus A is equal to resultant. A plus B plus C is equal to A plus B plus C. So grouping doesn't matter. You can take A and B and add them together first and then add C to it, or you can take B and C and add them together first and then add B to it. All of it's the same. It's all equal to R, the resultant. Okay, so that's a special word and it means the sum of vectors. So how do we add vectors graphically? So let's say we're given this vector here is A, and this vector here is B, and we want to know what is A plus B. Well, this is not helpful. Our model for how to add vectors was this head to tail trip that we took earlier, right? When we laid the first vector down, and then at the head of that one, we put the second vector, and then at the head of that one, we put the third vector, and then we just drew from the very first tail to the very last head. And that's true for, 84,000 vectors. So you can do it for anything, any number of them, right? That's our only model. But when we take into consideration the other rule, I'm assuming I move this perfectly, so it's still the same magnitude and direction. I'm assuming I move this perfectly, so it's still the same magnitude and direction. You can see I screwed up a little bit, but let's pretend like I didn't. Okay. Now, our rule says we can move vectors any way we like, and as long as I don't stretch them or compress them or change their angle, then it's okay. So I'm going to imagine this one's got a little ring on it, and it's going to slide it right along here. And then I'm going to do the same thing and put a little ring on this one and slide it right along here. Now what I've done is created a parallelogram. Big word, P-A-R-A-L-L-E-L-O-G-R-A-M. But by doing so, you can now see that I have vector B. There's its tail. I go to the head of vector B, and there's the tail of A. And then there's the head of A. So you can hopefully automatically see, oh, okay. So this vector is B plus A, because that's the order in which I added it, right? I did the B first, and then I did the A. So that's the vector B plus A. Now, if I went this way, I would go A, and then at the head of A, I found the tail of B, and it would be B. So you can see in this case, this is actually A plus B. But again, we already said that A plus B is equal to B plus A, but that's what you do. If the two vectors are tail to tail, then you complete the parallelogram. And draw from the common tail to the common head. From common tail to the common head. You see here, both A and B have their head up here. Both A and B have their tail over here. So the A plus B is just that. Okay. If you're lucky enough to be giving them this way, then you just draw from the tail to the head. Okay. So that's head to tail So when you're doing that, if it's head to tail, you just draw from the first tail to the very last head. So the next question is, what about subtraction? Graphically again. Well, when you subtract vectors, that requires us to recall something from algebra that you probably thought was the stupidest thing ever, and there was no reason to know it. It was A minus B is equal to A plus the opposite of B. That's true too with vectors. So now I can put the vector symbol over them. Notice I'm putting arrows over top of them. Your book generally uses, well, most books generally use bold print to indicate a vector as compared to regular print for its magnitude or for just a variable. It's hard for us to draw in bold print, so we use a little arrow over top of it. There's other ways too. But this right here tells you all you need to know. It tells you that A minus B is defined to be, so you can even put it this way with a defined to be, A plus the opposite of B. This is read opposite of B. What does opposite mean? It means you turn it around backwards. Okay. So that could also mean add 180 degrees. Or it could mean subtract 180 degrees. Doesn't matter whichever one you want to choose, but just changing the direction by 180 degrees makes it the opposite. So now if I have two vectors that are tail to tail, and let's say this is A and this is B, and I want to know what is A minus B. I know that A minus B is defined to be A, is defined to be A plus the opposite of B. So I've got B labeled. All I have to do now is say, this is negative B. Notice I took two vectors that were head to tail, and now all of a sudden they've become that were tail to tail. Now they've become two vectors that are head to tail. And I just have to add them. So my sum is this. This is A plus the opposite of B, which is defined to be A minus B. Does that make sense to everyone? What if they were automatically head to tail? So let's say this is head to tail. And I want to know what is A minus B. Okay, I've still got to use the definition that says that A minus B is A plus the opposite of B. So this time I'm going to use a different color because I noticed the blue didn't show up that boldly from the black. So I'm going to say now this is minus B, right? Now I've got to use that other rule. Remember, I can move a vector anywhere I wish as long as I don't change its magnitude and direction. So I'm going to slide this vector right along here and write this as A. Now I've got A plus the opposite of B, and I can see that that is, in fact, from the tail to the head, this is A plus negative B, which is defined to be A minus B. Does that make sense?
So what you just did there, you made it so that the A's head went to B's tail with the negative.
Exactly.
Does it always have to be like that?
It doesn't always have to be like that. Like I showed you here, they could be tail to tail. But in order to do a tail to tail addition, which is what I was showing you over here, you have to complete the parallelogram. So if this was negative B, the guy that points this way, and this was A, then A plus B, or A plus the opposite of B, would be from here to here, because I completed the parallelogram. So that's the big rule. When you're adding vectors, you either go head to tail, which is easy, and you just draw it from the tail of the first to the head of the last, like I did here. Or if they're tail to tail, that's more difficult to add because you got to complete the parallelogram and then go from the common tail to the common head. That's addition. Subtraction is actually easier when they're tail to tail, because when they're tail to tail, you flip B and automatically they become head to tail, and you can just complete it going from tail to head. But when they're head to tail, it gets more complicated. You got to do something almost like completing the parallelogram again.
Okay, gotcha.
That makes sense. Okay.
Yeah.
So those are the way, and believe it or not, this graphical technique, especially if you're using AutoCAD, like the actual software that you use to do computer-aided drafting and design, this would give you exactly the right answers to your vectors, to your vector problems. And if you even tried to do it just to scale, using a good scale, maybe some graphing paper, a protractor, and a straight edge with a ruler, you could actually get really good results within a few percent of the right answers just by drawing them out graphically. So this is, in fact, a very robust way to add vectors. But I'm going to show you another way that's even cleaner, and you don't even have to draw diagrams. You should draw diagrams, but you don't have to technically. Okay, so there's the graphical addition of vectors. Now what I want to say is some general things about vectors. General features of vectors. Or I'll call it vector algebra. We've already started a little bit of it. I told you, for instance, A plus B is equal to B plus A. So it's commutative. And I'm just saying that to remind you, hey, this is a word you used to know, right? I'm not going to require you to know that word. It's also distributive, or not distributive, I should say it's associative. And there's also other mathematical operations you can do. So scalar multiplication. So C times A, for instance. Okay. If you multiply a scalar by a vector, let's say this is our vector A. Okay. If the scalar is less than 1, let's say we'll say 1/2 A. I'm trying to make sure I match it pretty well. That's the vector 1/2 A. You see that its magnitude is just shrunk by a factor of 2. Okay. If, however, you multiplied it by a number bigger than 1, then you get that. And this is supposed to be 1.5 times longer. So it should be this. They go further, plus this. So that, and then that, yeah, it looks pretty good. Okay. So let's say this is 1 unit. This is 1/2 unit. And this is 1.5 unit. Okay. Now, if you multiplied it by a negative number, then you just get A pointing in the opposite direction.
Excuse me, Professor.
Yes, sir.
So I kind of just want to like reiterate so I understand what's going on here. So when we're talking about the magnitude and the vector, right? That's the length and the angle, right?
The magnitude and direction is the length and the angle. So the magnitude is the length in some sense.
Yeah, and the
direction
angle
is whatever angle and whatever coordinate system you use. Yes.
according to the x-axis, right?
Well, with
'Cause
those
like-
additional ways that we do it, but yeah, like normally if I just say at 30 degrees, then you know that's measured counterclockwise from the positive x-axis. But all those other ways I can say it are true too, and you got to be prepared for those. That's why I gave you that little bit about the compass and stuff.
Okay.
Okay, but yeah, you're thinking right. It's just a little bit bigger than what you're used to in pre-calculus or trig or whatever, because we're going to do a lot of different ways to specify angles.
Okay, so you can't change the angle, but you can change the direction in which the tail is going.
Exactly.
That way you can add and subtract.
Yep.
Okay.
Yep.
Okay, that makes sense. Thank you.
No problem. And this actually, once we know all of this, then we can do really smart things. We can say, for instance, if I have a vector, that we can decompose a vector into parts. So for instance, I could have an x-axis right here and a y-axis right here. And let's say we have a vector that is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So I'm going to try to draw one very specifically and try to get it fairly accurately drawn. Okay, let's say that is a vector A. Okay, this is called resolving vectors, or excuse me, this is called, let me call it, there was another word they like to use. I call it resolving them into components, but you could say breaking into components. Because there's really a beautiful way of adding and subtracting and stuff like that if you have them in terms of components, because you can sort of, use your rules of algebra, which says that, you cannot add 3x plus 2y. The answer is just 3x plus 2y, because x and y are not like terms. The 3x and the 2y are not like terms, so you can't add them. But you can add a 2x to a 5x or a 3y to a 12y, right? So if we think of vectors in that way, we might invent something that is exactly 1 unit long. So let's say we invent a vector that's 1 unit long and is parallel to the x-axis. We might call this x, and we'll put a little hat over it, because the hat tells everybody, hey, this is 1 unit long. In fact, this is a common notation that we use in physics, but normally in math, you learned it as I hat. and I say it's 1 unit long, I mean 1 unit. It's not one, it's 1 unit like this. It's not 1 meter, it's not 1 Newton, it's 1 unit. Then you can create another one over here that's parallel to the y-axis, and that one would be called y hat, or y'all probably know it as j hat. When we have that, now we've got a bevy of things that we can use to specify A. We can say A is equal to, notice, 1, 2, 3 units long. So this would be 3 I hat, because we learned that if I multiply a scalar by a vector, we just increase its length by that factor. So 3i is exactly how long this is. This one's 1, 2, 3, 4. J. Okay. Another way we could write that is 3 x hat plus 4 y hat. That's acceptable as well. And then an easier notation. See, it looks like a coordinate point. Remember, points are x comma y, but vectors can be less than number or component x, component y, component z, separated by commas, and then a greater than symbol. So those are all ways you can do it. And if you had a vector b, let's say b was now I can write b. You guys tell me what you think b is, if you can see it on the paper good enough here. I'm gonna bring it up a little closer to you in case there's any more vision problems. Can y'all see that that b goes over 1, 2, 3, 4, and up it goes 1, 2. So please now write b in your notes in the 3 ways that I just wrote it. A. Okay, hopefully everybody got 4 I hat plus 2 j hat. Hopefully you also did the x hat and y hat notation, which would be 4 x hat plus 2 y hat. And hopefully you did the less than greater than notation, which would be 4, 2. Okay. Now, if you want to add a plus b, you just add like terms. So 3 plus 4 is 7 I hat, and 4 plus 2 is 6 j hat. Negative b is just multiplying by -1, and that means you got to use the distributive property. So it's -4, -2. That's the easiest way to write it. And I only had that much paper left, so I decided to do it that way. So if I want to do a minus b, that's defined to be a plus the opposite of b. So I'm going to go 3 plus -4 is -1. And I'll go 4 plus -2 is 2. That's a minus b.
Professor, would those be the same numbers if you took the a vector and moved it to the head of the b vector?
Yeah, that's a very important point. That's exactly what I meant. You don't change this vector just by moving it around. As long as you keep the length the same and the direction the same, you can move it. So I could just move this a, the head of it to the tail of b, I mean to the head of the tail of it to the head of b, and then draw it there, and then I'd get this solution that would be 7i plus 6j. And if you do that on graph paper, you'll see it's completely obvious. Just use whole numbers like this, and you can write a and b next to each other, and then you can write a right at this particular spot, as if there's a new y-axis right there and a new x-axis right there, and you'll see that you get exactly what we got, which was 7i plus 6j. I'm glad you asked that. That's the first time anybody ever asked that. But yeah, that's exactly the whole point is graphically, you're allowed to move those around because this is just a vector, not a vector field. And we're not going to deal with vector fields until you're ready to deal with vector fields. So you don't even have to think about them until you start hearing me things like, say things like the electric field or the gravitational field and stuff like that. Okay. So that's sort of how we go about adding vectors, is we just add like components. You could also do, by the way, one more neat one. Let's say 3b minus a. Well, 3b, I'm just going to take the b and multiply it by 3. That means you got to distribute it. So I'm going to call it 12, 6. And then minus a is going to be plus the negative of a. And a, of course, was 3, 4. So this becomes 12, 6 plus negative 3, negative 4. 12 plus negative 3 is 9. And then 6 plus negative 4 is 2. That's the smallest way you could write it. Again, I prefer writing in I hat, J hat notation, but I had this little bit of paper and I wanted to show you one further example. If you look at the end of chapter 3, you'll see a bunch of simple examples of adding vectors. I say you do as many of those as you possibly can, and life will be good. Okay, meaning that you'll have enough of a good skill set where you can do this, because adding vectors, unlike in a lot of classes, you'll learn this neat mathematical technique, let's say completing a fraction or something weird like that, and then you won't use it again until the final exam. Adding vectors you're going to use every day from this class forward to all of your physics classes, all of your statics classes, all of your dynamics classes. You're going to continue to add vectors. So they're never going, that's not ever going away. Any questions on that? All right. Now that we have those ideas in our mind, you might want to think of this 3i. The 3 is the x component of a. The 4 is the y component of a. And in fact, components can be negative, like the x component of negative b is negative 4. The y component of negative b is negative 2. So components can be negative. So keep that in mind. Components but the magnitude of a component is still positive. So if someone asks you, what's the magnitude of the x component, you're going to say a positive number, no matter what. Okay. Now, normally we're just giving a vector. Let's say A is equal to 5.00 newtons at let's say 56.1 degrees. Okay. And let's say B is, let's say B is 10 newtons at 30 degrees. Now let's say it's, I'm not going to do 10. I want to say 2.0 newtons at 30 degrees. Those of you who might recall some stuff from trig probably know exactly why I'm doing that. Okay. What I want to know is, what is A plus B And then what is A minus B? Okay. So how do we add such vectors? Well, we draw them. We say there's X, there's Y. Since this says just blindly 56.1 degrees, I know they mean it's measured from the positive X-axis and they're measuring it counterclockwise. So what I do, and again, this is me trying to make the graphical part look as real as possible. I'm going to, in fact, decide on a scale to use, and I'm going to, in fact, use a protractor to measure the angles, but this is not graphical addition. I'm just showing you how you would do it in the case of graphical addition. So this is 50, this is 55. This isn't the best protractor. It doesn't even have single degrees. It kind of stinks in that sense. So I'm going to say this is about 56.1, say. So now I'm going to put this vector right here and say it's definitely along this line. Okay. Well, what scale shall I use? I'm going to use 1/2 of a centimeter is equal to 1 Newton. So now I can go up here and say, I'm going to make this vector 2.5 centimeters long. So that's my vector A. Okay. Now I can take a break from that for a second and imagine a vertically shot laser shooting down. Oh, excuse me. I got to show the effect. You got to make those weird noises. You really don't. But what that leaves is a shadow on the x-axis. And this is the magnitude of the x component. And in fact, a horizontal laser would leave a length like this, but it'd be over here, of course, but you can put it in either place. That would be the magnitude of the y component. So you might want to know, how do we find it? Well, we know this angle right here is 56.1 degrees, right? And we know from trigonometry this is the adjacent side, this is the opposite side, and this is the hypotenuse, whose y always gets left off by me. And then I use some old horse came hopping through our alley. Or you could use so ka toa. Okay. So I see sine of theta is equal to opposite over hypotenuse. That's supposed to be P over hypotenuse. Cosine theta is equal to adjacent. Dang it, I keep leaving off the middle letter over hypotenuse. And tangent theta is equal to opposite over adjacent. Okay. So now looking at that, I can see that the sine of 56.1, and I want you to do this. Take the time to write sine and cosine of each vector you have until you get really comfortable with it. And I'll see that sine of 56.1 is opposite, which is the what we call a sub y, over the hypotenuse, which is the magnitude 5.00 newtons. And then I'd write cosine of 56.1 is equal to adjacent, which is the x component. So I'll say a sub x over 5.00 newtons. So I can now figure out that a sub y is equal to 5.00 newtons times the sine of 56.1 degrees. which of course happens to give me 4.00 newtons. And A sub x is 5.00 newtons times the cosine of 56.1 degrees. And that, of course, happens to give me 3.00 newtons. And I knew that because this is a 3, 4, 5 triangle. And this is supposed to be what, 33.9 or something like that. Now let me double check my angles just in case. Sometimes I forget the angle, and I didn't take the time to do a, oh crap, I didn't take the time to do a check of it. But I'm going to do the inverse tangent 4 divided by 3. 53.1. Sorry about that, everybody. It's supposed to be 53.1, not 56.1. I knew that was coming up when I tried to write this other angle. So everybody change your 56.1 to 53.1 and write that as Mr. Younger is a goober. Or choose your own adjective. Okay, so these are all becoming 53.1. And 53.1, and then you'll get the actual right answers that you were supposed to get. So yeah, this is supposed to be 53.1 degrees, and this one's 36.9. So that's a triangle I often use. I hadn't planned on using it today, but I did it the last minute. So that's why I didn't refresh myself on exactly what angle it is. Another one that comes in handy, of course, is the 60-90 triangle, 60-30-90 triangle. The 60 is opposite the largest side, which is the square root of 3, which is about 1.73. And this is 1 and this is 2. So that's another good triangle to use, is the 60-30-90 triangle. And that's actually what I was using for B. So now if I drew B, using the same scale, of course, that has to be 2 newtons at 30 degrees. So I stick my protractor right here. I try to line it up where the center of that little hole is exactly on where the X and Y axes cross. And I'm using my X axis as if that's true as one of these lines. So I go up to 30 degrees, which should be right about here. And I know the vector is going to be parallel to this. But now 2 centimeters or 2 newtons is supposed to be 1 whole centimeter. So I'm going to make the mark right here. So I know that's vector B. Again, that's 30 degrees though. So now I can see that the sine of 30 degrees is equal to this guy, which is B sub Y, over the hypotenuse, which is 2.0 newtons, and cosine of 30 degrees is this guy, which would be the X component, over 2.0 newtons. So B sub X is going to be 2 times the cosine of 30. Well, if I look over here, cosine of 30, that's supposed to be square root of 3 divided by 2, which is 0.866. So it's 2.0 newtons times 0.866, some other stuff. So when I do that, again, that just avoids the work of having to do all the sine stuff and calculate it. I'm going to go ahead and calculate it anyways, though. I'm going to say sine, or excuse me, cosine. Everybody knows what the sine would be. Cosine 30 degrees. And I'll multiply that by 2 newtons. and I get 1.73, duh. And it is in the positive direction. That's something you have to take into account if you're ever outside of the first quadrant. You know, over here, I have a second quadrant, which has a negative X, but a positive Y. Then down here, I have a third quadrant that has a negative X and a negative Y. And then here I have a negative Y, but a positive X. So you've got to force those signs in yourself. Don't let the trig functions do it. Just automatically always take the sign of the nearest, the angle between the vector and the nearest axis, and then put your sign in by brute force. By is going to be, of course, sine 30, which everybody can tell is 1/2. So 1/2 of 2 newtons is 1.0 newtons. So now I have everything I need. If I want to know what A plus B is, all I have to do is add like components. Well, the X component of A was 3 newtons. The X component of B is 1.73. So that's 4.73 carrying 1 extra sig fig newtons in the I hat direction. And the B component would be the B component of, or excuse me, the Y component would be the Y component of A, which is 4 newtons, plus the Y component of B, which is 1 newton. So 4 plus 1 is 5. So that'd be plus 5.00 carrying 1 extra sig fig in the J hat direction, which of course you can also write as 4.73 newtons, 5.00 newtons, or you could even write it as 4.73 comma 5.00 and then put your newton after it. That would be acceptable as well. If I wanted A minus B, which was what the other part of the problem was asking for, A minus B, that's just going to be, I've got an AX, which is 3.00 newtons, and an AY, which was 4.00 newtons. Once I got that stupid 53.1 right instead of 56.1. And then I'll say minus B. Well, B we found was 1.73 newtons, comma 1.00 newtons, carrying an extra sig fig there. So now you can just do 3 minus 1.73. And my calculator's dead. 3 minus 1.73 would be 2 plus, or 2.27.
1.27.
Thank you. Oh yeah, because I did 3. Yeah, okay. I was doing 4 for some reason. All right, yeah, 1.27. Thank you. Newtons, and then 4 minus 1. I can do that one even. Maybe it's 3.00 newtons, again carrying an extra digit. So that's really the process you go through to add vectors and stuff like that. The key though is to remember a vector here in the first quadrant has both X and Y components being positive. A vector here has the Y component positive, but the X component is negative. A vector here has a negative X component and a negative Y component. And then a vector here, say, has a positive X component, but a negative Y component. That's the only thing that makes for students making simple little errors is they often forget that. So what I always do is I always take the angle that's closest to the vector from whatever axis it is. And when you do it that way, it's not always going to be like it was here. Sine is not always going to give you the Y, and cosine is not going to always give you the X. So you got to really take the time to write what is sine, what is cosine, and then put a sign, put an actual sign on it to indicate this is going to be positive, this is going to be positive. And then you just use the angle with no signs for it, and take the sine of it, take the cosine of it, find your components and add it. Now, what I want you guys to do, class is over 2 minutes ago, y'all are free to go. The rest of this will be on the recording though. I want you to go onto my YouTube channel and look at what I called the world's greatest vector addition problem. I want you to look at what I called graphically adding vectors and graphically subtracting vectors. And again, I want you to really look hard at that greatest vector addition problem. It's not the greatest in any real sense. It's more a matter of me showing you all the different ways you can specify vectors. You know, how all those different ways I showed you what the direction was. So definitely check that out. That'll be good practice. You can write down the original problem after you've watched it. Write down the problem, what vectors you're adding, and then add them and see if you come up with the same answer. That's probably the best practice you can get on doing vectors, on adding vectors. Okay. You guys have a good one. I'll see you at 1:30, and hopefully by then the practice tests and the online test will be available.
Professor, I have a quick question.
Yes, sir.
So with the test that's coming up, is that just on chapter 1 and 2?
Yes, sir.
Okay, cool. Do you have any like do you know off the top of your head the YouTube videos that will help out with that test?
You could look at all the ones that say well, basically all the ones up until today's date, because we started chapter 3 today. But there's a lot of other ones related to kinematics. So if you see, there's one that says kinematics, and it's got an aircraft carrier and a Tesla flannel, or whatever the name of that Tesla is. Those are good problems. And yeah, all our tests are generally going to be about 2 chapters long until we get to midterm and final.
Okay, appreciate it, Professor.
If you look in the order in my names of the document that I gave you that has all the titles, those titles are in the order in which the book goes. So anything that happens before you get to projectile motion would be good videos in that list.
Okay, appreciate it.
No problem. Anyone else? All right, well, I will see everybody at lab, and then other than that, I will see everybody at our next class on Thursday. So have a good day. Delaney, do you have anything?